Before 1973, exploring the cosmos via radio waves labored under a severe handicap: inadequate resolution. Early radio telescopes, hamstrung by their comparatively limited size relative to the vast wavelengths they sought to capture, produced fuzzy, indistinct images of the heavens. This limitation obscured individual radio sources and blurred the broader picture of the universe painted in radio frequencies. It prevented discernment of discrete objects from the cosmic background noise. Navigating this blurry landscape demanded a paradigm shift. Two pioneering figures, Ryle and Antony Hewish, stood poised to usher in this new era. Even prior to 1973, they had begun to establish themselves. Their prior work had established them as leading figures in the field of radio astronomy. They now sought to address this critical need for enhanced resolution. The central problem, then, was clear mapping the radio sky with sufficient clarity to resolve individual celestial objects. They needed to differentiate between distinct sources and comprehend their intrinsic nature. What were these radio-emitting entities? How were they distributed across the vast expanse of space? Did their spatial arrangement hold clues about the universe's grand structure and its evolutionary history? The answers lay hidden behind a veil of radio noise. The intellectual and technological climate of the early 1970s proved unexpectedly fertile ground. Advances in electronics, computing, and signal processing converged to make high-resolution radio surveys newly feasible. The necessary tools were finally available. The concept of aperture synthesis emerged as a particularly potent technique. It held the promise of overcoming the inherent limitations of single-dish telescopes. Aperture synthesis, in essence, involves combining data from multiple smaller antennas spread across a wide area to simulate a much larger telescope. This, in effect, increases its effective aperture. By meticulously correlating the signals received by these individual antennas, astronomers could reconstruct a high-resolution image of the radio sky. This method circumvents the immense engineering challenges and prohibitive costs of building a single, gargantuan radio dish. The basic methodology of the 1973 survey followed a meticulous plan. It involved performing precise interferometric observations, applying sophisticated data reduction techniques, and compiling a comprehensive catalogue of observed radio sources. Interferometric observations involve using multiple radio telescopes in tandem and interferometer, measuring the difference in arrival time and phase of radio waves at each telescope. Sophisticated correlation of the signals provides information on the spatial structure of the radio emission. Data reduction techniques correct for instrumental effects, atmospheric distortions, and other sources of noise, refining the raw data into calibrated visibilities. Source catalog generation involved systematic scanning of the sky, identifying peaks in the radio emission, and cataloging these points as individual radio sources. Positional data and flux density measurements were included for each object. This detailed catalogue acted as a foundation for further studies. The survey sought to verify or refute specific claims concerning the nature and distribution of radio sources. A key area of investigation focused on source counts. These involved determining the number of radio sources observed as a function of their flux density brightness. Different cosmological models predicted distinct source count distributions. A steady-state universe, for instance, would predict a flatter distribution compared to an evolving universe where source density was higher at earlier times. The survey thus aimed to provide observational constraints on the validity of these competing models. The results either would support or challenge them. Prior radio astronomy surveys, notably those conducted at Cambridge, had laid the groundwork for the 1973 effort. However, they also possessed notable shortcomings. The earlier surveys often suffered from limited resolution and sensitivity, hampering their ability to probe the fainter and more distant reaches of the universe. The 1973 survey directly addressed these shortcomings. It incorporated innovative techniques to improve both resolution and sensitivity. The aperture synthesis method itself, as implemented by Ryle and Hewish, represented a significant leap forward in resolution compared to earlier instruments. One key technical challenge involved mitigating the effects of sidelobe confusion. Radio telescopes, like any optical instrument, are subject to diffraction. This means that they are sensitive to radio waves arriving from directions slightly off from the intended target area. These aphaxis responses, known as sidelobes, can lead to spurious detections and increased noise in the resulting images. Ryle and Hewish developed advanced calibration and deconvolution algorithms to meticulously remove these sidelobe artifacts, improving the accuracy and reliability of their survey results. Their approach, which utilized advanced data processing techniques, represented a major innovation in radio astronomy. It allowed them to produce significantly cleaner and more detailed maps of the radio sky than had previously been attainable. This meticulous attention to detail and rigorous data analysis set a new standard for radio astronomy surveys and paved the way for future advancements in the field. The 1973 high-resolution radio survey of the sky, conducted by Ryle and Antony Hewish, yielded a wealth of information that profoundly influenced the trajectory of radio astronomy and cosmology. The survey's results, meticulously extracted and analyzed from observations, presented source counts as a function of flux density, identifications of radio galaxies and quasars, and new constraints on cosmological models. These findings, taken as a whole, provided substantial evidence against steady-state universe models, bolstering support for an evolving cosmos. A central element of the survey lay in quantifying the number of radio sources detected at different flux densities. This relationship, commonly referred to as the source count, held crucial information about the distribution and evolution of radio sources across cosmic time. The 1973 survey revealed a significant excess of faint sources at higher flux densities than predicted by steady-state cosmology. Steady-state, at the time, posited a universe unchanging in its overall properties, a universe where new matter continuously creates new galaxies to occupy any voids created by expansion. The observed excess of faint sources indicated an evolving universe where the density, or luminosity, of radio sources changes with time. Numerous individual radio sources discovered and analyzed by the survey have proven invaluable to extragalactic astronomy. The identification of bright quasars at high redshifts, distances so vast that their light has taken billions of years to reach us, provided critical benchmarks for probing the early universe. By studying the spectra and properties of these distant objects, astronomers gained insights into the physical conditions and processes occurring in the early universe, including the formation of galaxies and the evolution of active galactic nuclei. Despite its groundbreaking contributions, the 1973 survey did face limitations. Sensitivity limits constrained the detection of extremely faint sources. Systematic errors inherent in any observational endeavor introduced uncertainties in the flux density measurements and source positions. Challenges in source identification, particularly in crowded regions of the sky, complicated the task of distinguishing individual sources and determining their true nature. These limitations recognized, Ryle and Hewish incorporated methods to address these concerns. To mitigate sensitivity limits, they spent longer periods observing each patch of sky. By increasing the integration time, they increased the ability to detect weaker signals buried in the noise. They used calibration techniques to minimize systematic errors. These techniques include comparing their measurements with well-established standard sources and applying corrections to account for instrumental effects. They also implemented sophisticated image processing algorithms to resolve sources in confused regions, utilizing deconvolution techniques to separate overlapping signals. The legacy of the 1973 survey resonates throughout the field of radio astronomy. Its findings and techniques served as a foundation for subsequent research, inspiring the development of larger and more sensitive radio telescopes, the Very Large Array, the Atacama Large Millimeter Submillimeter Array, and other advanced facilities owe their existence, in part, to the pioneering efforts of Ryle, Hewish, and their team. The survey also spurred the refinement of aperture synthesis techniques, enabling astronomers to create ever more detailed and accurate maps of the radio sky. One notable example of a subsequent research project that directly built upon the 1973 survey involves the follow-up study of a particular class of radio sources catalogued in the initial survey. These follow-up studies, conducted with more sensitive telescopes and advanced observational techniques, investigated the physical properties of these sources in greater detail, examining their radio spectra, polarization characteristics, and spatial structures. These investigations revealed valuable insights into the nature of these sources, including their emission mechanisms, magnetic field configurations, and the environments in which they reside. The 1973 high-resolution radio survey of the sky stands as a testament to the power of meticulous observation, rigorous data analysis, and innovative techniques. Its contributions to our understanding of the radio sky and its influence on subsequent generations of astronomers remain undeniable. The survey played a formative role in shaping the development of cosmology and astrophysics, providing essential evidence for an evolving universe and fueling the search for ever more distant and exotic celestial objects. The impact of the 1973 survey persists despite the advent of far more advanced telescopes and surveys. The survey provided a baseline against which subsequent observations could be compared, offering a glimpse into the evolution of the radio sky over time. Its catalogue of radio sources continues to be a valuable resource for astronomers, serving as a starting point for new investigations and providing a historical context for understanding the dynamic nature of the universe. The detailed source catalogue generated by Ryle and Hewish represents a lasting contribution, enabling identification and study of a multitude of objects. This foundation laid the groundwork for further research into the nature and distribution of radio sources, impacting our overall understanding of cosmic evolution.